What's up, class? Today we're going to be talking about floating point arithmetic. So basically we're going to be going through how IEEE format stores floating point numbers, and also how we're going to retrieve a floating point number from the memory by converting the values in the memory of the IEEE format. So a quick overview of the floating point arithmetic in the IEEE format. First of all, it's represented in scientific notation. And why do you want to use scientific notations? Is because instead of writing out the number bit by bit, we are representing just part of the number, and then we are doing some multiplications by timing it to, for example, in our daily lives, like 10, we have a base 10 system, times 10 to like some power. In binary, we're multiplying a number with 2 to like some power. So in that case, we can store a huge dynamic range of numbers instead of by using a relatively small number of spaces like bits, and also because we're multiplying it with a large enough with a 2 to something power number, the relative position across the whole range would be maintained the same. So the current standard that we're using is set by IEEE, and then it allows us to do like high accuracy computations, and also that every single bit has its own functionality. And also one of the biggest challenges in floating point arithmetic is how do we deal with the precision and lower bit accuracy. And IEEE formatting does allow us to maintain high accuracy even in like lower bits. And also just because it's really stable, we can always we always know what's going to happen next, and then how to do the calculations. We can handle the exceptional errors more we know, and it's predictable, and it's a more reasonable behavior. So let's take a look at the IEEE floating point format. So when we want to write a number in our base 10 system that we use in daily lives, we can use it just bit by bit, but we can also just write it out in like some number between 1 to 10, but not 10, you can't get to 10, times 10 to like some power. Same case, whereas for binary systems, it's just going to be 1 point something number times 2 to some base. So in that case, in the IEEE floating point format, we use 32 bits to represent that number, and then we take that scientific notation, we dissect it, and then store it into each part of our floating point memory. So it consists of 3 parts. The first thing is our single sign bit. It is the most significant bit, the 31st bit, and it denotes a positive number if it's 0, and it denotes a negative number if it's 1. And then we have 8 bits following it. It's called exponent. For exponent, we use a thing called the bias-based 127 encoding. By doing so, basically it's just like adding 127 to the number we're trying to encode, and we put that into our exponent, the 8 bits. By doing so, we don't have to work with like 2's complement, because we are supposed to be able to deal with from negative 127 to negative 128 to 127, and by using this bias-based 127 encoding, we don't have to deal with negative numbers. All we have to do is just calculate it, treat it as an unsigned number, and then we just minus 127, and then we will get to the exponent we want to get. And then we have our next 23 bits, and that's going to be called the significant. Some people also call it the mantissa. It is the 23 most significant bits that is after the decimal point. So for a number like 1.10111 something, we look only for the numbers after decimal points, so we only store, and then we don't store a number before a decimal point, because that number has to be 1 when we're doing a binary storage. So if we take a look at this example, we have a signed bit 0, that means it's positive. We also have an exponent 8 bits like that, but the actual exponent is we have to decode this number, and then we have to minus by 127, and in that way we'll get the actual exponent we're trying to look after. And also here is significant, or the mantissa, the 23 bits, is the most significant 23 bits after the decimal point. And then as I just mentioned earlier, we neglect the bits before the decimal point because it can only be 1, and it has to be 1. So the actual mantissa is actually 1.010101 and followed by a bunch of zeros. All right? So let's do an example. We have a floating point number in base 10 called 10.625, and then when we convert it to binary expressions, it's 1010, which is 10, and after decimal it's 101. Right? So just like any scientific notation numbers, we can just time with the base. We can change the exponent, and we can shift this decimal point around. So if we just shift this decimal point to the left 3 bits, we have to multiply 2 to the 3 because it's base 2. And then we get 1.010101. So what will be our sign bit? Our sign bit, because it will be 0 because it is a positive number. And our exponent, because it's 3. And as we said, we have to use a bias base 127 encoding. We have to add 127 to get the actual number we're trying to encode. So the actual number we're trying to encode is actually 3 plus 127, which is 130. And if we turn it into binary, it's this number over here. For the sign bit, as I mentioned, it's positive. And then we have the mantissa. We neglect the number before the decimal point, and we only store the number back here, which is 010101. So 010101. And then the other bits are just followed by zeros because we don't care about that. So this number over here is a representation of 10.625 in IEEE floating point format. So how do we convert this number back to 10.625? First of all, we determine the sign bit. It's a 0, so it's a positive number. And then we calculate exponent. 10010 in binary is actually 130 and in base 10. So we minus it by 127 and we get 3. So that's our actual exponent we're trying to get. And then don't forget to add the mantissa, add a 1 in front, because that we are always neglecting the number before decimal number, that decimal point. So this is very crucial. A lot of people will forget it. So remember to add this 1, and that's the actual mantissa that we're looking for. And then if you combine all those together, we have a positive sign, our mantissa, and then we also have an exponent to that exponent power. And then we can calculate that back to here, and then we know it's 10.625. So that is how IEEE floating point format stores a number and how we can get the number back from IEEE format.